Hello, good evening, my dear students. Welcome to Gradeup, India's biggest e-learning platform. This is Sooraj Gopi. I welcome you all to this very important and interesting class of LMTD method. Okay, so very good evening. Quickly join the session and please do let me know whether my audio and video is proper and you are able to understand the voice and audio in a proper way. No lagging, no issues. Good evening, guys. Good evening. Good evening. And quickly join the session because today's session will be very interesting one. Very good evening. Okay, so today we'll be talking about LMTD method and I will be discussing questions from this topic and how the questions are coming from gate perspective from this topic that will be also be discussing. Okay, so very good evening. I hope so all of you like this topic and please do share this video with your friends and do hit a like on this video because all of you will be liking this session because this is a very important one. Okay, fine. Let me introduce about myself. My name is Sooraj Gopi. I have more than 5 years of teaching experience. Master in thermal science, mentored 15,000 plus aspirant for GATE, ESE and SSHE. I am expertise in mechanics, thermal applied heat transfer, industrial and theory of machine. Okay, fine. So the first question you should be asking is, sir, what do you mean by heat exchanger? Anyone who can tell me what do you mean by heat exchanger? Anyone? What do you mean by heat exchanger? By the name itself, we can say it's basically a device which is used to exchange heat between two different fluids at different temperatures. Are you getting the point? Because in order to have a heat exchange, you should be having different temperatures. So basically what is happening, there are two flowing fluids and there's an exchange of heat between these fluids and we call it as heat exchanger. If you see on your screen, good evening Kalam, good evening Kalam. Okay, so it is used to heat from it used to transfer heat from a hot fluid to a cold fluid. As a result, hot fluid temperature decreases and the cold fluid temperature will increase. Okay, you are well Morgan. Okay, hello, good evening, well Morgan. So can you tell me the example, or if you're seeing on the screen, what is this device called? Definitely it's an heat exchanger. Can you tell me where we are using this kind of device? This is basically a heat exchanger. Have you ever come across this device? Raju, Velmurugan, anywhere in your daily life have ever observed this kind of a device, like in your house or nearby to your home or anywhere? Anyone who can respond to this problem? Okay, so basically you definitely might have used, very good, you might have seen in your backside of the refrigerator. If you have observed on the backside of the refrigerator, exactly, exactly, if you observed on the backside of the refrigerator or at the front side of the car, that place we call it as a radiator. Okay, radiator or refrigerator backside, these all are this all are basically the examples of a heat exchanger. Okay, fridge, very good. On the back side of the fridge, definitely you might have observed, you might have seen there's some hot or temperature of the back side of the fridge is very high. If you have ever observed that, they have written, please do not touch when it's in operational. Why? Because the temperature of that tube will be very high. Okay, there's a chances that you could get a skin burn. So basically this is being used in order to exchange heat from hot fluid to cold fluid. This kind of device we are calling it as heat exchanger. Very easy, very now if I broadly classify any heat exchanger, we are having three basic classification or three basic types. One is parallel flow, counter flow and a cross flow. Anyone who can tell me what is a parallel flow? Parallel flow is basically when hot fluid and cold fluid both are moving in the same direction. If you see, observe this, hot fluid and cold fluid both are moving in the same direction. We are calling this as a parallel flow. Okay, now if you observe in this case, what is happening, this is a cold fluid moving from left to right and there's a hot fluid moving from right to left. So this is nothing but a counter flow. This is nothing but an example of a counter flow. Okay, and what is an example of a cross flow? This one fluid is moving like this and second fluid is moving like this. So basically both fluids are moving perpendicular to each other. This type of flow we call it as cross flow. Can you give me the example of a cross flow, daily life example? Example of a cross flow. Example of a cross flow is a radiator. Because in a radiator what is basically happening, we'll be having a fluid, okay, which will be moving from like this, fine, and we'll be having some tubes through which second fluid will be moving. So basically what is happening, you're having one fluid moving like this, second fluid moving like this, both are perpendicular to each other. So whenever a hot fluid and cold fluid are moving perpendicular to each other, we are calling that as a cross flow. If they're moving in the same direction, we are calling that as a parallel flow, and if they're moving in the opposite direction, we are calling that as a counter flow. Okay, now let us try to quickly understand, if we are having a parallel flow, then what will happen? What will be the temperature profile of a parallel flow? If you observe, this is a shell and tube heat exchanger. In this, there is a fluid A. Let us suppose this is fluid A and this is fluid B, which is moving in the same direction. They are both moving in the same direction. So if I say hot fluid will be losing heat to the cold fluid, and cold fluid will be rising, the temperature will be rising. So this is your temperature profile of a parallel flow, or also known as co-current flow. Okay, fine. Is this clear? So this is your T hot inlet, this is your T hot outlet, this is your T cold inlet, and this is your T cold outlet. So basically what is happening, if I say the basic funda of a heat exchanger is hot fluid will be losing heat and cold fluid will be gaining heat. And one more thing very important, this is an adiabatic device. What we are assuming is all the heat which is lost by the hot fluid will be gained by the cold fluid. Okay, so we will be saying this heat exchanger is nothing but a adiabatic device. It's nothing but a adiabatic device. Okay, clear? A temperature profile for a parallel flow. Same thing. If you're drawing for a counter flow, this will be for a counter flow. Counter flow, opposite direction. Opposite direction. If you are observing this, hot fluid, cold fluid, both are moving in opposite direction. So this type of flow, and this is the temperature profile. This is your hot inlet. This is your temperature of hot outlet. This is your cold outlet, and this is your temperature of cold inlet. Okay, so both fluid are moving opposite to each other. And one more thing you always remember, we always are having an exponential decrement and increment of temperature in case of a heat exchanger. Okay, always remember this point. And they have asked in ESE for 1 mark, so definitely you can expect this question for 1 mark in gate examination. Okay, fine. now let's go for the analysis of heat exchanger. That means what you have to do whenever you are getting a question. Okay, first and foremost equation is energy balance equation. What is energy balance equation? That means all the heat which is lost by a hot fluid, that will be gained by a cold fluid. That means heat lost by hot fluid will be equal to the heat gained by the cold fluid. Heat gained by cold fluid. Okay, now that means we are basically are more enthalpy gain. If you say in thermodynamics point of view, we are having an enthalpy drop and enthalpy gain. Okay, so what we can say that m dot h cph thi minus tho should be equal to m dot c cpc tco minus tci. This we call it as energy balance equation, and this you can apply in any heat exchanger. This you can apply in any heat exchanger. That could be a counter flow, that could be a parallel flow, that could be a cross flow also. Are you getting the point? Okay, the heat lost by the hot fluid, that the same heat will be gained by the cold fluid. This is your energy balance equation, which you can apply in any heat exchanger, and this is very fruitful and very useful equation. Now let's talk about LMTD. Now what is this LMTD? Why we are stating this term as LMTD? Okay, now if I say this is a heat exchanger, let us suppose this is x equal to 0 and this is x to L. So when you're moving away from the starting point, let us say this is your starting point, and always we are defining a starting point with respect to the hot fluid. This is your hot fluid, this is your cold fluid. Okay, so as you are moving along the length of the heat exchanger, what you are observing that the temperature drop is constantly varying. At the starting, the delta T is very high. At the end, the delta T is very low. So at each and every point, we can say that delta T is a function of X. Are you getting the point? Your temperature drop is nothing but a function of X. Of X, that means we can say if I take the average of all this delta, if you take the average of all these delta, that average we are calling it as logarithmic mean temperature difference or simply mean temperature difference. If you read the statement, it replaces the variable temperature difference between the hot fluid and cold fluid by a constant temperature difference such that the heat transfer which will be having the same heat transfer as that of at individual point. And what we have seen that Q, which was previously equal to this heat transfer, is equal to U into A into delta Tm, where delta Tm is logarithmic mean temperature difference. What is U? Overall heat transfer coefficient. Why? Because in this case we are having a combination of conduction and convection both. So definitely we have to take into account the single entity which we are defining, and we are calling that as overall heat transfer coefficient. Now area is the surface area of the heat exchanger. Q is the heat transfer. Either you can calculate Q from this formula or you can calculate, okay. Now the main problem is how to calculate this delta Tm, which we call it as LMTD, How to calculate this delta Tm? For this, the very important, let us suppose if you're having a parallel flow, okay, this is your hot outlet, this is your hot inlet, this is your cold outlet, and this is your cold inlet. Okay, let us suppose this temperature difference I'm taking it as T delta To, this temperature difference I'm taking it as delta Ti. So LMTD of parallel flow is equal to delta Ti minus delta To divided by ln delta Ti by delta To. So from this expression, we can calculate the LMTD for a parallel flow, and you can apply this Q is equal to UA delta Tm and get the value of heat transfer. Okay, but if I talk about counter flow, let me hide this. If I talk about counter flow, this is your hot fluid and this is your cold fluid. This is your THO, this is your TCI, this is your TH inlet, and this is your TC outlet. Okay, temperature difference, this is delta To and this is delta Ti. What we have observed that the counter flow LMTD is also equal to delta Ti minus delta To divided by ln delta Ti by delta To. Okay, is this clear? So by these two expression, are we saying that both LMTD are same for counter flow and parallel flow? Is that so? No, my dear students, both counter flow and parallel flow both are having different LMTD, because if you observe closely, what is delta Ti? It's the difference between Thi minus Tci. And what is delta To? That is Tho minus Tco. But if I talk about counter flow, the delta Ti is Thi minus Tco and delta To is Tho minus Tci. Okay, so the basic formula is same, but if you go in detail, the formula is entirely different. And what we have observed that the LMTD for a counter flow is always greater than equal to LMTD of a parallel flow. Okay, important concept, 1 marks question. We are coming across some special cases. Okay, now let us talk about a condenser. Can you tell me which of the fluid, condenser and evaporator, basically we are talking about a phase change phenomena. Phase change phenomena. So if I'm talking about a condenser, can anyone tell me which of the fluid is undergoing a phase change? Is this a hot fluid or a cold fluid? Is this a hot fluid or a cold fluid? Anyone? If I'm talking about a condenser, that means the fluid is losing heat. And which fluid lose heat? It's a hot fluid. So we'll be drawing a straight line because temperature, there is no temperature difference. So hot fluid will be undergoing a phase change, and this is your cold fluid. Ultimately, you'll be getting the answer. And what we have observed that whenever we are having a phase change, your parallel flow, parallel flow and counter flow both will be same. Both will be same, will be having same response. That means LMTD of counter flow and parallel flow both will be same if you are talking about phase change phenomena. So it doesn't matter if you are drawing the equation like this or if you are drawing this like this. Ultimately, you will be getting the same result. Condenser, the fluid is losing heat, and definitely hot fluid loses heat. Okay, is this clear? Imran, very good. No, it won't be cold fluid, it will be hot fluid. But if I talk about evaporator means the fluid is taking heat to convert its phase, evaporate. So definitely we are talking about a cold fluid. We are talking about a cold fluid. Okay. So this is your hot fluid and this is your cold fluid. This is your cold fluid. Okay. So whenever we are talking about a phase change phenomena, always remember that a parallel flow or counter flow both will be ending with the same result. So it doesn't matter by which approach you are going, either we are going with a parallel flow or counter flow, ultimately we will be getting the same result. Okay, there is one more special case, then we'll be solving some questions. That is a special case in counter flow. Okay, after that we'll be solving some questions. Special case of counter flow. Let us suppose if I say the heat capacity of hot fluid is equal to the heat capacity of cold fluid. Heat capacity of cold fluid. If this is happening, then definitely we can say THI minus THO is equal to TCO minus TCI, because both m dot Cp will be cancelling out. Because what is heat capacity? This is the product of mass flow rate and specific. The same by energy balance, we can cancel out, and ultimately we are getting this result. Or we can say THI minus TCO is equal to THO minus TCI. This is nothing but delta Ti and this is delta TO. That means in a counter flow, what we are getting, LMTD, we are getting 0 by 0 form, indeterminate. So whenever we are having this case, when mass flow rate or heat capacity is same, we will be having LMTD will be equal to delta Ti will be equal to delta TO. Very interesting, important conclusion, because this type of heat exchanger, we are calling it as balanced heat exchanger, and this is only possible in counter flow. Okay, if in the question they are stating it as it's a balanced heat exchanger, by default we'll be assuming they will be having same heat capacity, and if I draw the temperature profile, it will be straight line, two parallel line which are straight. This is THI, THO, TCI and TCO. Is this clear? So this is a complete gist of LMTD method. In, I would say, 18 minutes I have completed LMTD. Now we'll be solving some questions from this topic so that you can improvise your concept, and let's see how much you have understood from this topic, because I am constantly saying in every session, this year, that is 2021, IIT Bombay, the heat transfer weightage will be very high. Okay, so make sure you are ready with your preparation, and let's try to solve some questions from this topic of LMTD. Are you ready, guys? Quickly, I want a response from all of you. Mukil, Raju, Devari, Imran, Mukesh, Velmurugan. So shall we solve some question? Let's proceed. Let us start with some easy problem, and let's see how many of you are able to answer it easily. In a heat exchanger, it is observed that delta T1 is equal to delta T2, where delta T1 is the temperature difference between the single phase of fluid at one end, and delta T2 is the temperature difference at the other end. Okay, this heat exchanger is quickly, very good, very good. I want everyone to respond. This heat exchanger is Imran, Maurya, Velmurugan. Okay, so I hope so. Now you have got enough time to respond. Now in the question, what they are saying, let us suppose I'm having let us suppose I'm having a hot fluid which is going like this. Okay, and what they are saying that the temperature difference, that is delta T1, is equal to the temperature difference, that is delta T2. This is only possible in which heat exchanger? This is only possible, my dear friend, in the counter flow heat exchanger, precisely We are talking about a balanced heat exchanger. Remember, just now we have discussed, this is nothing but we are talking about a balanced heat exchanger. Option C. Very good. Mukil, Maurya, correct answer. Correct answer. Okay, and please do share this video and like this video so that all of your friends will be benefited from this video. Next question. Okay, in a condenser of power plant, the steam condenses at temperature of 60 degrees Celsius. The cooling water enters at 30 degree and leaves at 45. Tell me what will be the logarithmic mean temperature difference, LMTD, of that condenser. Easy question, direct formula based. So we are having a, but in this question, if you observe, they have not stated whether it's a parallel flow or a counter flow. So anyone who can help me out in this, what will be the type of flow? Parallel flow or counter flow? Or anything will be giving you the same result. You go with parallel flow or counter flow, you take up any heat exchanger, you'll be getting the same result. Yes. Sir, if I say there is a phase change, steam condenses, that means there is a phase change phenomena. So it doesn't matter are we taking a parallel flow or counter flow, because we are coming across with a special case, that is phase change. So let's go with the parallel flow. Now steam condensation, that means the fluid is losing heat. Let us go for hot fluid. This is your steam condensation. Enters at 30 and leaves at 45. This is 30. This is 45. Very good, Maurya. And this is 60. So let's take, this is 30 degree. This is 15 degree. Calculate LMTD. Easy question. LMTD is equal to 30 minus 15 divided by ln 30 by 15. And my dear friends, heat exchanger is that topic. This is the most simplest and scoring topic in the heat transfer subject. Why? Because they will be asking you questions only for 2 marks. Okay, this they will be asking not 1 marks, but maximum of the time they will be asking from the 2 marks problem. Okay, so this is 15 by ln2. What is ln2? Some of the values you should always remember. ln2 is approximately 0.696. So 15 by 696, you will be getting 21.6 degrees Celsius. Option B. Okay, you will be getting 21.6. Option B is the correct answer. Very good, Mukil. Well, Murugan, correct answer. Okay, clear? Let's proceed for the next question. Steam in a condenser of a thermal power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water, which enters a tube at the condenser at 14 degrees Celsius and exits at 22. That means again same problem, steam condensation. That means a phase change phenomena. This is a 30 degree, again 30 degree. This is your cold fluid entering at 14 degrees Celsius and exit at 22 degrees Celsius. So what you have to calculate? You have to calculate the heat transfer. Okay, U value is given as 2000 watt per meter square Kelvin. Fine. And area is given as 50 meter square. So quickly, you know that Q is equal to UA into delta Tm. And delta Tm we can easily calculate. Delta Tm is equal to, this will be 30 minus 14, 16 degree. 16 degrees Celsius, this is 8 degrees. We'll be having 16 minus 8 divided by ln 16 by 8. Again ln2. This is 8 by ln2. So we'll be getting Q is equal to 2000 into 50 into 8 by ln2. Okay. So, and you have to calculate in megawatt. So into 10 to the power minus 6, you'll be getting in megawatt. Tell me what is the answer you're getting. Approximately, if I cross check, up to 2 decimal, it will be 1.15 megawatt. So answer 15 megawatt. Exactly. Very good, Maurya. Correct answer. Very good. 1.15 megawatt is the correct answer. Very good. Easy question. Okay. Very good, Nisha. Correct. Mukil? I hope so this is clear, because maximum cases you will be coming across with the phase change phenomena questions. Exactly. If I say approximately 1.154, so that is your correct answer. Up to 2 decimal, 1.15 is the correct answer. Next question. Okay, in a counterflow heat exchanger, hot fluid enters at 60 and cold fluid leaves at 30. So we are having a counterflow. We are having a counterflow. Let's draw the temperature profile. The hot fluid enters at 60 degrees Celsius and cold fluid leaves at 30 degrees Celsius. The mass flow rate of hot fluid is equal to 1 kg per second and mass flow rate of cold fluid is equal to 2 kg per second. Specific heat of hot fluid is equal to 10 kilojoule per kg Kelvin and specific heat of cold fluid is equal to 5 kilojoule per kg Kelvin. The question is, you have to calculate log mean temperature. You won't believe this question was of 2 marks in the gate examination. Let's see how many of you are able to answer this. Now for LMTD, you should be having 4 temperatures being given. And in this problem, only 2 temperatures given. How to calculate LMTD? How to proceed? So if you observe closely, if I multiply m dot h cph value, if I calculate this m dot h cph, this is equal to 1 into 10. This is basically equal to 10. Leave the units. M dot c cpc, because both are having same units, it is 2 into 5, which is equal to 10. Can you tell me which case we are talking about? So this is ch, capital ch, this is capital cc. That means heat capacity of the hot fluid and cold fluid are same. That means what is the type of heat exchanger? This is a type of balanced, this is basically balanced heat exchanger. And for balanced heat exchanger, just now we have seen that delta Ti is equal to delta To is equal to delta Tm. So directly this is 30 degree. So this 30 is, you can place E is the correct answer. Okay, already we have seen for a balanced heat flow, balanced heat exchanger, if we are talking about balanced heat exchanger, we'll be getting delta Ti is equal to delta To is equal to LMTD. That is why they have only given 2 temperatures. Option B, very good. So I can now redraw this diagram, because now I know that this is a balanced heat exchanger. That will be straight two parallel lines. Straight two parallel lines. Because earlier I didn't know. So what I did, I drew a very generalized counterflow. But after that, when I found out that it's a balanced heat exchanger, I have rectified my diagram. Okay, is this clear? Option B is the correct answer. And my dear friends, from LMTD, you are getting these type of questions only. Next, let's see what is the next question. In a condenser, water enters and flow at a rate of 15 kg per hour. Condensing steam is a temperature of 120. Now we are having again a phase change phenomena. Condensing steam. So let's draw. Condensing steam means you can draw for a parallel flow, counter flow, it doesn't matter. So let's draw. This is 120 and this is also 120. Okay, cooling water enters at 30. It enters at 30 degrees Celsius and leaves at 80 degrees Celsius. Okay, mass flow rate of water, that means cold fluid, is equal to 1500 kg per hour. Specific heat of water, that means CPC, is equal to 4.187 kilojoule per kg Kelvin. Overall heat transfer coefficient U value is given as 2000 watt per meter square Kelvin. You have to calculate the area. How to calculate this area? Sir, I don't know that. If I knew the heat transfer, I can directly use Q is equal to U into A into delta Tm. I can calculate delta Tm, U is given, but how to calculate this Q? Is there any method I can go for the calculation of the Q? By looking at this given data, can you tell me how to calculate this Q, heat transfer? Sir, we know that the mass flow rate of the cold fluid and mass flow rate of the cold fluid and its specific heat is given, and also the temperature drop is given. So I can directly relate it as m dot c cpc tco minus tci is equal to u into a into delta tm. Okay, so if I manage to get the value of delta Tm, I can get the value of area. So let's calculate delta Tm. This is 120 and 30. So this will be 90 and this will be 40. Okay, clear? So your delta Tm will be equal to 90 minus 40 divided by ln 9 by 4. Place this value and you'll be getting the answer. Now make sure you are converting into SI. This is 1500 by 3600. Cp is 4187. I've converted into joule per kg Kelvin. TCO is 80, TCI is 30, U is 2000. Area you have to calculate. Delta Tm is 50 divided by ln 9 by 4. So when you calculate this, tell me what is the value you are getting, A, B, C or D. This and this will be cancelling out. 50 will be cancelling out. Okay, you can cancel out these two zeros and ultimately you will be getting, this is a calculation based problem, 0.707 meter square. Please cross check it and do let me know. You will be getting option A as the correct answer. You'll be getting option A as a correct answer. Very good. Absolutely correct. Okay, option A is the correct answer. Fine. Fine, let's proceed for the next question. We have to complete the entire segment of LMTD today, and after this session you will not be having any doubt left out with you. Next question. Air enters a counterflow heat exchanger at 70 degree and leaves at 40. Water enters at 30 and leaves at 50. What is the LMTD value? Sir, it's a counterflow direct, and this question was asked in GATE 2000 for 2 marks. You won't believe this question was asked for 2 marks. So this is 70, 40, 30, 50. So this is 20, this is 10. So delta Tm LMTD is equal to 20 minus 10 by ln 2. So this is 10 by 0.697. So approximately what is the answer you're getting? Approximately what is the answer? Very easy. We can round off to 0.7. So this will be 100 by 7. So this will be 140. Will be having 4, 5, approximately 14. Option B. Approximately 14 is the correct answer. Very good, well Murugan. Option B. You have to calculate because this will save your time. Definitely calculators are allowed. So why to use calculators if you get the answer by doing the approximation? Okay, make sure you are doing approximation whenever you are getting time, because it will save your time in the GATE examination. Very good. Sheshav, Maurya, Mokil, KK, very good. Option B is the correct answer. Absolutely correct. Let's proceed for the next question. Okay, this is a 1 marks problem from the previous year GATE, and this question was also asked in ESE. Let's see how many of you will to answer it correctly. A correction of LMTD is necessary in case of cross flow, parallel flow, counter flow, or all of the above. Correction factor, where we are using correction factor in LMTD? I need quick response from all of you. They are saying LMTD of parallel flow, counter flow, or cross flow. If you have ever heard about this term, LMTD of cross flow is equal to F times LMTD of counter flow. Okay, and this F is basically the correction factor. This is nothing but the correction factor. Okay, and this way you are getting from the heat transfer data book. Okay, we are having standard data like for a particular counter flow heat exchanger, for a particular combination of atmospheric pressure and temperatures, we are getting the cross flow. Fine. So option A, very good, Maurya. Correct answer, option. So because we are using this correction factor only in the case of cross flow. Okay, we are using the correction factor only in case of cross flow, because for counter flow and for parallel flow, we do have the formulas with us. So it doesn't matter like are we going with a parallel flow or counter flow, but yeah, it definitely matters when we are talking about a cross flow. Good evening, Mehboob. Okay, next question. LMTD in case of counter flow heat exchanger as compared to parallel flow heat exchanger is. Can anyone tell me the answer of this? LMTD in case of parallel flow heat exchanger as compared to the parallel flow is higher, lower, same or none. If this would have been an MSQ question, let us suppose this is an MSQ question, then what will be your answer? If this is an MSQ question, multiple select problem, then what will be your answer? A, B, C or D? Definitely A is correct. If this is an MSQ problem, then definitely you can go for option C also. Why? Because we know that LMTD of counter is greater than equal to LMTD of parallel. We know that LMTD of counter is greater than LMTD of parallel. This we know, this is a generalized formula. But if I say LMTD of counter equal to LMTD of parallel, can you tell me the case when this is happening? This is basically happening whenever we are having a phase change phenomena. Phase change. Okay, whenever we are having a phase change, then the LMTD of counter flow and parallel flow both are same. So this was question from an MSQ point of view. Very good, Kalam. I say, well, Murugan. Very good. Very good. Clear? Done? Let's proceed for the next question. Okay. For evaporators and condenser, for a given condition, the logarithmic mean temperature difference for parallel flow is, again, same question, now been asked in a different format. Evaporators and condensers. That means we are talking about a phase change phenomena. Then LMTD of the parallel flow is equal to counter flow, greater than counter flow, smaller than counter flow, or very much smaller than that of counter flow. A, B, C or D? Easy questions. Anyone? Whenever we are having a phase change phenomena, we know that just now we have seen LMTD of counter is equal to LMTD of parallel. Option A. Very good, Mukil. Correct answer. Option A. Is this clear? Very good, Maurya, Velmurugan, correct. Option A is the correct answer. Okay, let's proceed. Let's proceed for the next question. I hope, yeah, this was the last question of the day. I hope so you have clarified your doubt and you have improved your understanding from this topic of LMTD. Let me brief you about the very important 3 courses which Gradeup has launched. That is Gear Up Gate Mechanical, Rank Up Gate and Vision 2020. Gear Up is basically for those students who want to revise the entire syllabus of GATE in a very shorter span. You'll be having theory plus practice. Okay. Rank Up is mostly based on the practice session. That means who want to improve the GATE score, those who are writing this examination in the 2021. And this Vision 2022 is a course for ESN GATE 2022, ideal for second and third years. Those who are aiming for GATE and ESC in the year of 2022. So any doubt you can call to this number. And these are the Gradeup achievers who have secured in the top 100. And if you are becoming a member of the Gradeup Super, you will be having an access to all the courses. That means Gear Up Gate, Rank Up Gate, Vision. So if you are becoming this member of Gradeup Super, you will be having access to all the courses, doubt resolution, and also you will be having a member of Green Card. That means you can give the mock test, subject test, everything. So one-stop solution, go for Gradeup Super, you'll be having access to all the entities. So for cost point of view, Gradeup is providing EMI options for 6 months 2000, for 12 months 1400, and for yeah. Yes, sir, UPPSC AE mechanical के लिए कोई class? Yes, if I say this is AE foundation course is there. AE foundation course is there. Okay, those who are aiming to write in 2021 next year. And also there is score booster. score booster who are writing this UPPSC exam in December 2020. December 2020, those who are writing exam. So for that, there are free classes going on. Free classes going on YouTube as well as on the Gradeup app. Okay. So make sure you are joining this, and if I talk the timing of this, I'm taking at 11 a.m. in the app. At present, I'm taking heat transfer because heat transfer is also a very important subject for UPPSC point of view. Clear? So this is the entire free classes, and this is a Foundation is a course, complete structure course. So I hope so it was helpful. Make sure you all are joining with me tomorrow in the app class also 11 a.m. in the heat transfer. This all are free classes. Okay, take the best benefit, and also on the Gradeup app there are like PDFs of the classes. There are like notes which you can download free of course, nothing, no payment, nothing required, only just you have to install the app and get the benefit. Okay, classes, notes, what else you want? Free test also Gradeup is providing. Exactly. This time you can expect heat transfer because if you do the analysis, I've already did an analysis from IIT Bombay's previous four time they have conducted, and heat transfer weightage was continuously increasing every year. Okay, so make sure you are ready with your sources, you're ready with your knowledge to crack this gate 2021. I hope so you all like the session, and make sure you are subscribing to this channel, and we'll meet next time. Next topic will be NTU method because we have discussed LMTD. Next will be NTU. So see you soon. Till then, enjoy your day and good night. Take care and stay safe. Bye bye.